Hello, everyone. So my name is Zach. I'm last minute subbing for Carola. Hopefully, I can be at least half as interesting. But today, basically, I want to talk about general lessons that we've been tackling as classical imaging people and as AI has been coming along and we've been sort of adapting to it. I mean, I come from, I guess the image doesn't render, but there was an image of our group, which is a very large one. It's just a 40-minute train away from here. Yeah, I'm just here at the bottom. And we have lots of collaborations with a lot of institutions and also funding from them. But basically today I want to talk about is basically what we work on, what that whole list of people actually work on, which is a lot of real world, but also modeling problems that we get whenever we start talking about imaging problems. So these are things like reconstructions, restorations, segmentations, motion estimation, because in the real world there's a lot of issues and lots of possible applications where we would want to use better and more improved methods for this. I mean, the simplest example that you can think about is, for example, this. So imagine you are observing something on the left, but what you actually want is something on the right. In the real world, there's noise, there is undersampling issues, there is opposeness that comes around. And this is technically the problem in almost any applications that you consider. So things like denoising, segmentation, reconstruction, classification, all of them extract we extract some sort of unexpected information. And what we want is, in an automated and robust way, get the reconstructions that we can actually use in downstream tasks, for example, in medical imaging. And there are many exciting applications. Again, I don't know what's happening with the images that we, and broadly as a group, have been working on. And I mean, there is Under as well who can sort of attest to a lot of these. And if you're interested in talking about any of them, please do. And let's chat about them. But the reason we've been looking at so many different applications is because a lot of the people in our group are mathematicians. And what you end up finding is whatever application you come across, whatever sort of problem, whatever physics you come across, it requires new sort of mathematics to do well and to really sort of overcome it. And the reason why is very simple. It's because real imaging data is complex, diverged, messy, and what we actually want for real-world applications is robustness. We want to be able to handle unseen data, to have almost zero training data, and still be able to be accurate and explainable as well as affordable. And this effectively, sort of all of these issues are something that's been sort of a limiting factor for actual adoption of AI in anything real world. Sort of beyond looking at chatbots. And so the way that I want you to think about this is there's basically two different paradigms. There's a paradigm of let's try to understand what's going on and really model and dig in. And then there's the paradigm of let's throw over parameterized models to try to get some information from data which we don't want to put in the effort of modeling. And that's effectively sort of, this is where we started and this is where we find ourselves nowadays more and more. And like the kind of things that you end up doing is relying a lot on sort of variational models, things basically surrounding sparsity, and on the right is basically just neural networks. And if you were to try starting to compare it, as I said already, you basically get this kind of, I don't know, pro and con chart. And if you take anything from this talk, take away this, right? It's whenever we start actually trying to understand what the model is, what the data is, we get a lot of very nice things. Things like generalizability, not requiring data, being able to be quite physical. And we actually get a lot of insight into the structure of the problem, which can sort of help in downstream tasks as well. But there are two big issues, and that is we are not as adaptive to data. So if there are changes in the data, we're not as good, and it's computationally demanding. Because a lot of the time, the more complex the models, the harder it is to deal with them. Whereas data-driven imaging, or basically AI, you basically lose all of the good ones, but you do recover the bad ones, right? So you suddenly become adaptive to data and extremely computationally efficient. We become able to actually solve the kind of problems we couldn't solve before, but on occasion. We can't do that reliably. And what we in the group have been really trying to work on is something in the middle, something that gets the best of both worlds, because that's exactly what we would want in a real life setting. I.e. basically also get this adaptive to data and computationally efficient. And just to give you an example of why this actually matters, and this I think is something that Carola likes to include in almost every talk nowadays. We were trying to create a new method, and we were trying to compare it for a very ill-posed problem. So this is extreme limited angle. You basically compute a tomography. You basically lose a slice, I think, of about 60 degrees. And so obviously, when you try to back project, you start getting really, really bad noising effects and limited data. So you can't just rely on the physics to be able to solve the problem. You really need to have some sort of prior knowledge about what kind of data you're dealing with. And what you find is, so here, these are two AI-based models that we have developed in the group and more broader. And what you find is, whenever you start just throwing AI at a problem, and then this is basically this learn primal dual, you start seeing lots of hallucinations. And effectively what these hallucinations are is you learn the wrong prior. Somehow the data that you had pointed in the wrong direction compared to what you were actually looking for. Whereas whenever we started sort of integrating and trying to do this in a sort of hybrid manner, whenever we still did some mathematical modeling but used AI in very specific places, you would see that you would avoid these hallucinations. And there's another point, which I think is the really big one, is the fact that by all metrics that we would actually consider, this is better, right? So I think there's a whole another problem of if we want to automate anything imaging, we need to really think about what kind of metrics we should be considering as well. And so the broader sort of hybrid idea is that we start relying on structure preserving deep learning. And whenever we start talking about biomedical imaging, it gets quite complicated because what is really structures? What kind of structures do we have? And so a lot of the work in our group has been more in the kind of problems where you actually get nice structures. So whenever you're trying to use deep learning for solving or discovering PDEs, you get a lot of structures, as a matter of fact, because you get a lot of symmetries, you get knowledge of the actual differential equation that you can try to sort of integrate into deep learning. And I mean, on a broader level, sort of adopting such a point of view also leads us to create better and more efficient deep learning, but that may be of slightly less interest here. And I mean, the most interesting one is going to be this one, the one that I'm going to talk about. And sort of in the context of inverse problems, the two things that we have been able to do, as I said before, is either put deep learning into mathematics. And so this is sort of the classical variational regularization framework, where T sort of is the physics, Y ends up being the observation, usually the noisy one, and then the regularization is the thing that sort of tries to basically suppress the noise, push it towards the prior, right? And the thing that we've been working on is directly sort of learning the regularizer from data. And I mean, that is technically very classical, but the use of over-parameterized networks has been quite new. And then on the other direction is trying to put more mathematics into deep learning. So whenever trying to do direct reconstruction, i.e. going from observation directly to the reconstruction using a network, you find a lot of the time that sort of giving more knowledge about the physics, trying to put it into the deep learning itself, tends to stabilize the problem in a lot of ways. And this has been quite successful in terms of sort of iterative reconstructions where you basically take your iterative method and you unroll it and then you parameterize everything. And a lot of times the constraints that you consider, so this is the hybrid part, it can be things like Lipschitzness, convexity, mass volume, positivity, preservation, and a lot of the time whenever we look at any specific problem, we know these a priori. We know that sort of in a lot of physical problems, nothing can be negative, for example, right? And this can be something that we could try to encode into the networks directly that we use. And just for context again, the reason why we're even looking at AI is because it can help, is because in a lot of very ill-posed problems, sort of having knowledge about the data, being able to say that the reconstructions that we're looking for should look in a very specific way can be very useful. And one particular one that I think we've been working on a lot in the group is in cryo-EM, where the signal-to-noise ratio is horrible. You shouldn't be able to reconstruct anything, but using prior knowledge can help a lot. And I mean, there are broader collaborations as well. These I'm not as familiar with. So yeah, but just to give you some mathematics now, maybe good for some parts of the audience. Effectively, what we talk about when we talk about learning regularizers is that you have some sort of physical model, forward model, which is usually noisy, and then to sort of stabilize, to regularize the problem, you add your regularizer here. And oftentimes, this is basically just the distance to your observation. And regularization, whenever we would approach the problem classically, sort of in this knowledge-driven paradigm, we would basically think, what kind of properties does the data have? Is the solution meant to be sparse? Is the solution meant to be sort of piecewise constant? And then we would design the regularizers according to that. However, all that does is effectively trying to put a different kind of prior. And those kind of priors we could try to extract using directly out of the data that we may have using machine learning. And effectively, so here, the point is that we are limited in what we can model. And so having that data to have an automatic way to extract some sort of prior information would be very useful. And so from left to right, these are effectively different understanding of our priors. I mean, realistically, this is sort of no prior. TV is total variation, i.e. sort of piecewise constant. And then AR is a machine learned one. Now, what do we expect to be able to get out of that? The reason why we've been actually looking at learning regularizers instead of learning sort of the reconstruction operator directly is because of interpretability and stability guarantees. Because I can mathematically prove to you that the reconstructions I get from this are going to be stable. They're going to be convergent. And I will tell you in a bit what exactly I mean by this. But what we basically get is interpretability, stability convergence. We can adapt the same sort of regularizer for different noise levels as well in a very, very natural and systematic way. Unlike a lot of the time, if you trained a neural network for one specific noise level, you cannot apply it for another noise level. And this also incorporates the forward model explicitly and incorporates the noise statistics in the regularization parameter itself. So effectively, instead of learning to reconstruct, you learn a prior directly and you have access to it directly. Now, the things that we would want out of any imaging reconstruction problem. So the first one is well-posedness, right? Existence, uniqueness, and continuity and stability. What I mean by this is if we have some sort of physics, here it's represented as K, and you know that sort of the observation is F, right? So here, what you want is that the solution is stable. So basically, if due to some sort of noising, you end up sort of slightly perturbing away from the actual observation, you want to make sure that you don't step completely away somewhere. You want to make sure that you are effectively continuous, that you are somewhere close to the reconstruction that you would want in the noiseless case. And that is the notion of stability. Uniqueness basically tells us that there's only one solution. So effectively, even if we have many different solutions, what our regularization is supposed to do is pick one of them only. Yeah, so this is basically uniqueness and continuity. Now, the other thing is we want to have strong prior information, or some call it, you can think about it as implicit bias as well. Because effectively, all three of these, they are very valid reconstructions. They all approximately satisfy the observations. Yet some of them we consider to be more realistic, some of them we consider to be less realistic, and ultimately it's that we're trying to capture with a lot of AI, what we consider to be realistic. Now, in the same way, what kind of models you use also matters a lot. And here is a very, very toy example. If you have some sort of spiral data, certain constraints on your networks can't actually capture it. So for example, if you were trying to learn a convex regularizer for this kind of data, you wouldn't really be able to, because the data itself is not convex. And so, I mean, here we're trying to learn the distance to the data as a function. what you end up finding is the convexity really breaks a lot of things. And what you end up having to find is some sort of middle ground that doesn't really break a lot of the things that you consider, but also sort of retains the performance. And so I guess I'll just continue, and I will show you exactly what I mean by this in a second. Now, the third thing is the idea of convergent regularizations. I will skip the wall of maths. I will explain to you exactly what I mean by this. And basically what it means is, as the noise level goes to 0, we should be reconstructing the real thing. And this effectively captures this. So basically what we do here is we start reducing the noise level. And what then we end up noticing is that we slowly start reconstructing the ground truth. And this is something for a lot of regularizers you can actually prove directly. And this is a very, very powerful property because it tells us we are doing the consistent thing. We're not adding random spurious features. And this is effectively the hallucination sort of limiter that we would be considering here. And I think the number 4 is interpretability, and I think this is really the biggest one. It's the fact that when stuff goes wrong, we know exactly the way in which it goes wrong, and we know how to detect it, and we know how to adapt to it. Because whatever we are considering, whatever regularization we are considering, there's always bias, right? You always pick one solution out of many. But knowing how to quantify that bias, knowing how to select parameters in a way that guarantees you don't end up using this bias, is sort of the distinguishing part about learning regularization versus learning to reconstruct directly. And I mean, the last part is the fact that it's meant to be efficiently computable. So whether you can rely on sort of smoothness and convexity properties, whether you have some sort of simple optimization algorithms that you can use to optimize this, all of these end up mattering in practice as well. And a lot of methods end up being certainly barred simply just because of this, a lot of interpretable methods. Now, there's a lot of information that you can find sort of in some of our works on sort of on a broader picture of when we were trying to really compare quite deeply a lot of different methods that have been appearing. Now, just to illustrate some images, because I mean it's an imaging talk, some tomography examples in sparse VUCT that's actually relying on deep learning, so this is sort of a classical knowledge-driven one, relying on deep learning can really improve a lot of the reconstructions that you end up considering, especially as you start taking it further and further and further. And I mean, here's the pyramidal. So sort of the intermediate conclusion would be that it works, but the question really ends up being whether it does, and it depends on what you mean by works. If you have sufficient and high quality training data, then it really doesn't matter too much which methods you end up doing. But theoretical guarantees only come from very certain methods. And ultimately, it's not just methods that we want to be developing. We want to be developing them for a specific purpose. And a lot of the time, just reconstructing is not enough to be good at segmentation downstream. What you want to do is some sort of joint task-adapted reconstruction. So emphasizing the features that you expect the downstream tasks to need. And coming back again to this example of hallucinations, any regularization, any sort of reconstruction, it introduces bias. And what we have as an issue is that deep learning bias is hard to understand at the moment. But classical regularization techniques, bias is relatively simple to understand. And this is something that I mentioned before, is you end up basically a lot of the time having some sort of stability versus performance guarantee, that the more structure you put in on your solutions, the more sort of guarantees you try to satisfy, you end up finding that the worse performance gets. All of these still, or I think most of them end up better than the classical solutions that we have at the moment, but still the stability and how to find this sort of middle ground between stability and performance is something that we've been searching for a very long time now. And ultimately, I think we need better mathematics. We need better understanding of what we're doing, how we're doing it, and what we should be relying on. Because we know that every single one of these things, training data set, parameterization, loss, optimizer, they all play a systematic role in how we model what we end up with. And what we don't have is that we don't really have good analysis of reconstruction properties. So a lot of the time, you are sort of searching for better and more applicable notions, actual mathematical notions, that would be more useful for what we're using AI for in practice. And the problems of interpretability and reverse engineering, and I mean, I think is another very interesting question. And so this is basically the end. Just the overall takeaway messages is deep learning is here to stay. I'm not trying to basically say that it's never going to make it into image reconstruction. It most definitely will, and it already has. But we really should be trying to think about how we apply it, what kind of prior knowledge we can include to really impose the stability, impose these guarantees that guarantee that what we're doing is actually coherent and it makes sense. Yeah, hopefully that makes sense. There you go.